Okay, so let's take a look at the modern atomic theory, which is part two in the series. You might recall that part one was a historical look at the development of the model or explanation of what the atom was all about. And that goes all the way back to Democritus and the Greeks. What this is going to address is the current modern view of what the atom structurally looks like. Now, we left off the history of the atom with the idea of the Bohr model. It was a very powerful explanation of what the atom looked like on the inside. Let's review this. In the Bohr model, it was viewed that electrons moved in specific circular orbits, just like the planets do in the solar system. There is each orbit or shell had a specific amount of energy associated with it. The electrons existed in their shells, and when they existed in their initial shells, we called that a ground state because the electrons were in the lowest possible energy level. And what could happen is electrons could jump from one shell or one energy level to another if in fact energy was provided, such as electricity or heat. And when they did this, they entered an excited state because they had more energy, and when the electrons fell back to their ground state, light or radiant energy got released. Here is a diagram or picture of what we just described. We can see here that there is an electron in the inner circle in blue, and energy is given to that electron, and the electron enters a state of excitation. The electron jumps to the next shell or energy level, and then what happens is the electron falls back to its original ground state, which you can see at the very end there, and here you see that the electron is back to where it was, but by falling back it has emitted a photon or energy packet. The real powerful thing of the Bohr model is that the electrons exist in a shell, and that the first shell, which is called N1, can contain 2 electrons, and then in the second shell, number 2, there are a maximum of 8 electrons that can fit, and as we just showed, the electrons can jump back and forth between the shells, giving off light when they fall back. And so this is the Bohr model description of the atom. This is again a diagram that shows the nucleus and the distribution of electrons in these shells. The problem with this diagram, again you see 2, 8, and 8 being the maximums. The problem with this model is that the distribution of the electrons becomes quite complex. Here we see borinium, named after Bohr, of course, and you can see the electrons distributed per given shell on out with a very large nucleus. But as I said, the Bohr model turned out to be wrong. It doesn't work. And the reason why it doesn't work is on the left you see a hydrogen atom. You see the blue nucleus and the green electron are going around the outside. And using this model, Bohr was able to calculate the amount of energy that the atom should get off when you give it electricity. The problem is that when you put 2 electrons in there, like helium, the calculation didn't work. It was assumed that it simply was a measurement error, but it turns out the mistake is that the Bohr model, the planetary model, in fact is not correct because the calculations in the end did not support it. So the question is, if this planetary system of the atom is not correct, what is? So what we see is it works only for hydrogen. They don't move in orbits. And the idea of energy coming out in blocks is correct, but it just did not support the model itself. So what became or got developed is a very, very complex description of what is now called the quantum wave mechanical model. And that quantum wave mechanical model is what we're going to explore in this unit. You may ask, why did we use the Bohr model throughout this entire course up until now? Why didn't we teach you the quantum wave mechanical order to begin with and use it? And the answer is because the mechanical model, though correct, is really rather complicated. And the Bohr model did let us explain so much of the chemistry that we needed, such as ionic bonds, covalent bonds, patterns of the periodic table, that use of the more precise quantum model was not necessary. And at this point, though, we do need to know the more accurate description, and that's what we're going to work at today. What it is that every electron in the quantum model, which was first described by Schrödinger, every electron is given a very, very specific location. Now, what that means is simply this. If you look at the Bohr model, the electrons are going around and around in shells. Within each shell, the electrons, in theory, should have been found. And these electrons are spinning around very rapidly. Well, it turns out that's not correct. Every single electron has a very, very specific location in that shell. And it's not simply going around randomly. And so the electrons have to be accounted for in terms of the location. And that electron is going to have a certain energy level or shell. It's going to have a subshell, and that subshell or orbital is going to have a specific orientation, and the electron has a certain spin. So what we're going to do is look at how every electron in a given atom has these four characteristics. And you're going to need to be able to know what of those four characteristics exists for every single electron. Now, Bohr clearly got right the first idea. Electrons do exist in energy levels, and those energy levels are assigned a number, N1, N2. And it should be noted that the further away the electron is from the nucleus, the shell number that it has indicates the amount of energy that it has. So the shells are given numbers 1, 2, 3. And the size or energy of the shell can be determined from the number given. So an electron in energy level 1 has less energy than the electron in energy 2, etc. So an electron first is assigned a energy level or shell number. That's 1, 2, 3, or 4, etc. Now, within each shell, the electrons are found in suborbitals. Those orbitals have certain shapes. The electrons do not go around and around. Rather, the electrons appear, disappear, and then reappear in another subshell place. So here we see what are called p orbitals. And what happens is there are 3 p orbitals. You will notice there are p orbitals on the z-axis, there are p orbitals on the y-axis, and finally p orbitals on the z-axis. Now in this case, the z orbitals, there are 2 regions. There's a region here and the region there. Now what happens is an electron can exist right here in this portion of the p orbital. But what happens is that electron disappears, it disintegrates, turns into pure energy, and then it reappears over on this region here, which momentarily it stays, then it disappears, and then reappears here. So what happens is you can have up to 2 electrons dipping in and dipping out of the p orbital in the z orientation. There are 2 more electrons that appear in the py subshells or orbitals. And so you see electron here would appear, disappear, and reappear here. Can this electron down here skip over to the z one? No. This electron is committed to the p orbital in the y. And of course you have the electrons appearing in the x. So what you have is electrons appear in a certain distance from the nucleus, which is called the shell. But within the shell, rather than going around and around like a planet, it in fact exists as a location where it appears or disappears in these different regions. Now, this is where it gets quite complex. How many different orbitals or subshells are there? The answer is within the p, there are orbitals in the x, there are orbitals in the y, and there are orbitals in the z. When you get to the d level, there's a much more larger set of orbitals that becomes possible. And bear in mind, what an orbital is it simply is a location where an electron can appear. And it can appear either in one or the other region that they are paired with. And there are a maximum of 2 electrons per orbital or subshell. So here you see up here with p, this is the px orbital, and you have up to 2 electrons dipping in, dipping out here, and those 2 can only be moving back and forth between these 2 locations. You have another 2 that can appear in the z location, and you can have a maximum of 2 appearing here. So notice within all the p orbitals, there's 2 px, 2 pz, 2 py, so the p orbitals can handle a maximum of 6. Now when you get to the d levels, it's become much more sophisticated. There are up to 5 different orientations or orbitals that can be held, so D can handle a maximum of 10 electrons among all its orbitals. And finally you get to an enormously complex arrangement referred to as the F orbitals. There are 7 different possible orbital orientation. Each orbital can have a maximum of 2. So the F can handle a maximum of 14 electrons. D a maximum of 10. P a maximum of 6. Finally the S, which is simply circular or spherical, that can handle a maximum of 2. So let's explore the idea that each orbital has different orientations. If you take the p orbital, there's px, py, and pz orbitals. Now what that simply means is that the orbitals themselves are oriented in locations relative to the coordinate system or coordinate plane. And electrons again can appear in this orbital or this orbital or this orbital. Any given orbital, such as the one right here, can only handle a maximum of 2 electrons. Now, why is it that only 2 electrons can appear in any given orbital? And the answer is because electrons have what is referred to as a spin. The electrons are spinning, and when they spin, they become little magnets. And when they're little magnets, those magnets either are oriented up, south, north, down, or if they spin the other direction, they spin with north being up, south being down. And so what you have is you have electrons, if they act like magnets, they cannot have the same spin in the same orbital, for like magnets, they will repel each other. And what we do is we represent the electron as having either a spin up or a spin down. So a given box represents an orbital, for example, a px orbital, or the box might represent a d orbital, and in that orbital only 2 electrons can exist, one spinning up and one spinning down. The rule says you draw the arrow up first in an orbital, and then you draw it down in the same orbital but in a different orientation. So let's take a look at this. You'll notice in the top one we've shown the 3 possible p orbitals. There's a px, there's the pz, and the py. Those are actually very hard to read. It's blurry, my apologies. But what we say is the px, this box represents this orbital. This box represents this orbital. And of course, this box is this orbital. So there are 3 different p orbitals, x, z, y. Into each of those orbitals, I can fit a maximum of 2 electrons. And we represent the electrons as a spin up or a spin down. Now, in the F, there's 1, 2, 3, 4, 5, 6. There are 7 different possible electron orbitals. So we have 1, 2, 3, 4, 5, 6, 7 boxes for the F orbital. And we will fill the electrons in that shell in that manner. So let's go back and review. Niels Bohr thought that the atom was a flat pancake and that the electrons go around like planets around the nucleus that has protons and neutrons. Each region was a shell, and there were a maximum number of in each shell. There were 2 in the first. There's a maximum of 8 in the second. But again, it appeared like a pancake. Now, Bohr's model was correct in that the electrons do appear in these shells. However, the idea of the electrons zipping around like planets around the sun, that is absolutely wrong. The electrons do not go around in a circle at all. Instead, the electrons are at a certain shell or distance, and the electrons, believe it or not, appear, disappear, and then reappear someplace else. And so the notion of the quantum mechanical model says that the electrons appear in orbitals or subshells. And when you see these shapes, what we're saying is these shapes, which are the orbitals, are regions that that electron can appear in. So you have it appearing here, it dips out, disappears, reappears here, dips out, reappears here. So these are regions that the electron will appear in. These two electrons can only appear in this area here. Two more electrons can appear in either this area or this area, etc. These electrons appear in a spin. Now what that means simply is this, that in the first orbital, which is the first shell, in the first shell I have a s orbital. I have two electrons. One electron spins up, one electron spins down. If I have more than two electrons, then what happens is the next electrons appear in the next region outside. Again, Bohr would say those are shells. So you do have a second shell, but the electrons would appear in the spin up, spin down of the s shell of the in the s orbital of the second shell. You then have in that second shell 3 p orbitals, and those p orbitals are oriented in the x, y, z, and the electrons appear in the up or the down based upon their spin. So notice every single electron is given a energy level, shell level 1. It is given a orbital, s's or p, and it's given a spin, up or down. So each electron has a very, very specific location. Now, we use a shorthand method for all of this. You will notice that here you have what is referred to as the first shell. In the first shell, you have the s orbital. In the s orbital, there are two electrons. So you have one in the front, s, and as a superscript, almost like an exponent, you list how many electrons there are present. What you then do is go to the next shell out. This is the second shell. In that second shell, you have the s orbital. The s orbital has two electrons in it. But if you have more electrons, you still have the you still have the second shell, but now the p orbitals become part of the locations, and you have a total of 6 electrons possible in the p. Notice it's all in the second shell. This, in fact, is called the electron configuration of neon. Because it's a noble gas, we put brackets around it. And so when the electron configuration of neon is requested, you would list it in this manner shown here. What this right here shows is the actual energies or location of each of the electrons. And if you were to ask to diagram where all these electrons actually appear, you would list them here. So this is the quantum mechanical model. Here is the actual space-filling orbitals. Here is the energy location of every electron. And this is the shorthand electron configuration listed here. And this now is the bracketing showing neon.